Good afternoon, everyone. My disclosure is that Harrison, Virtus, and Vitrolife have an ongoing collaboration agreement. So it's all started, 12 months ago, and I wasn't a doctor then. I was a medical student at the Sydney Children's Hospital and doing my pediatric rotation when Dr. Simon Cook, the scientific director of IVF Australia, came and gave the student a talk about IVF. And this is one of his slides, and he showed me this video of a human embryo growing in time-lapse for 5 days. And I was absolutely amazed by this. So of course, when everyone packed up and ready to go home, I walked down and said, Simon, look, I've been working on artificial intelligence. I think I can build you an algorithm that would select which embryo would make baby, which one wouldn't. And he was completely taken back by this. What is a medical student got anything to do with artificial intelligence? So since this is an IVF conference, there's obligatory baby photo. This is me in my dad-loving arms when I was 1 month old. And as you can see behind me is the computer. And it was one of the first personal computers in Ho Chi Minh City, Vietnam. And my parents are math teachers. So my dad, one of my earliest memories is my mom covering this computer with a plastic cover because the roof was leaking and the rain was coming through. So growing up, my father taught himself how to code. And on the right here is the first programming textbook in Vietnamese, which he has written himself and introduced programming as a subject in school in Vietnam, teaching kids how to code. So growing up, I always been interested in programming and even artificial intelligence, even though I didn't do a lot back then. And then I went to Australia and I met Paul Ramsey, a founder of Ramsey Healthcare. And it was fortunate in my life. He mentored me both in life and in work. And he said, Aengus, you can apply your skill to help people through medicine. And that's why I ended up in medical school in that fateful afternoon at the Sydney Children's Hospital. So Simon showed me the incubating machine, the embryoscope, and I was amazed by the technology. And I believe that AI can really transform the way we assess embryo through time-lapse. So let's take a step back. Why do we select embryo anyway? So if we have a robust way to select embryo, we can prioritize which one is the highest viability and transfer those one first. At the same time, we can rank embryo that undergo cryopreservation so that we have the optimal order for embryo transfer. And all of this led to shorter time to pregnancy. And when I was looking into this, there's a couple of ways that people go about doing this. So number one is morphological grading. So an expert embryologist, in this case Gardner and his colleague, has came up with a grading system based on their decades worth of knowledge. And a trained embryologist would learn how to perform this grading, an alphanumeric system. And they would look at one image, a snapshot of the developments, and produce this grading. The challenge with this is that, number one, we only look at one of the image across the whole time-lapse story. And two is that this is a very subjective and potentially time-consuming process. And there's a lot of variability between different embryologists, the way they grade embryo. And motivated by this, there's really a wave of time-lapse incubation where we are able to produce a video of an embryo developing over 5 days. But of course, the curse of this is we end up with way too much data, and it's really impossible for any human to look through all of these images. So we came up with morphokinetic algorithms. So once again, an expert embryologist would come up with various checkpoints, different timing events, and perform various annotation like T2, T4, T8, and so on. And then, once again, a trained embryologist will go and perform this annotation with high degree of subjectivities and variability. And then we can combine those timing information with known pregnancy outcome to come up with some statistical model, such as the KIT score, and be able to predict clinical pregnancy. Since the introduction of AI, there has been a lot of different tools, but once again, AI are not all the same. So one implementation of this is guided annotation with AI, such as the KIT score, where a model would look at the whole time-lapse videos and allow you to zoom in on different parts of the videos so that the annotation itself can be more standardized or more quicker. But once again, this only takes a problem one step back, because instead of a human annotating, we now have an AI annotating, and you're still limited by the imagination of the embryologist who came up with those annotations to begin with. So the performance of this AI model can never exceed that of the original underlying time-lapse algorithms. There's other work recently in Nature about an algorithm called Stork that would look at the single day 5 image and able to predict the grade of the embryo, be it good, fair, or poor quality. And once again, because this algorithm is trained on what the embryologist has said, it can, by definition, never exceed that performance of an embryologist. And once again, we're only moving the problem one step back because inherently the data point is still noisy and still variable. So when I started this journey, I asked myself, what was the wish list features of a good embryo selection algorithm using time-lapse? So number one, it really needs to be predicting a clinically relevant endpoint. Because embryo viability isn't one thing, it really is a spectrum ranging from things like time-lapse annotation to morphology or embryo quality, clinical pregnancy, fetal heart, and finally live birth. The more we move across this spectrum to the right, the more difficult it is for an AI algorithm to predict the outcome because of increased uncertainty. But the more clinically relevant you get. So I really settled on fetal heart because it's the most informative information and endpoint in terms of embryo quality, yet it reduced the noise associated with carrying a child through 9 months for live birth. Second, we want this model to be end-to-end, meaning that it doesn't have any proxy outcome and look at the raw time-lapse video and directly predict fetal heart pregnancy. It's a humbling approach in a sense that we want to say, let's just forget everything that we knew or thought we knew about embryo selection using time-lapse and let the model objectively look at the data and see what it can find out about embryo development. Number three, we want to fully utilize the time-lapse data that is available for us. So morphokinetics, such as time-lapse annotation, is in a sense one-dimensional. It only focusing on timing information and how long things take, basically. Morphology is two-dimensional. It looks at an image, which is 2D, and basically asks how good does the embryo look. Whereas time-lapse is 3D, right? It's morphodynamic. We're able to look at how the embryo behaves through times, and this is the kind of data we want to work with to fully utilize time-lapse. And of course, it needs to be sufficiently validated in a large cohort of patients. So we start with a large data set. So we call everybody we knew within the Virtus group. And if you are here today and you were involved in the process, thank you very much. It would have been possible without the international collaboration that Virtus had. The data came in from 8 different labs in Australia, Ireland, Denmark, and UK. There was 2 different incubating systems, 4 different cultures, extremely heterogeneous patient population that was collected, and there was no exclusion criteria whatsoever. The embryo is then labeled with clinical outcomes. So positive embryos are embryo that was transferred, resulted in a fetal heart. Negative embryos are embryo that either deemed unviable for transfer or that was transferred never created a fetal heart. And I encourage you to read our human reproduction papers for more details on how the methodology was set up. But the truth of it is this. We start tabula rasa, which is Latin for blank slate. We give IV, which is the artificial neural network, a full sequence time-lapse videos and ask it to predict the pregnancy outcome. Because it starts from a blank slate, it initially make a complete guess. In this case, let's just say 15%. It then compare that outcome with a known fetal heart outcome, in this case 100% for yes, and calculate what we call a loss, which is the difference between the two. Basically how wrong the model was with its prediction. It then used this loss to do backpropagation, a process where it continues to fine-tune the weight of the synapses within the artificial neuron so that it can become better and better at making a good prediction the next time around. And this process is repeated for hundreds and thousands of times and looping over the data set for multiple rounds. If you think about it, this is like doing hundreds and thousands of randomized controlled trial in simulation within a computer, because the model would come up with hypotheses of what features to look for, and then self-validating against the data to see, and finally arriving with a set of features that is proven to be predictive throughout its training process. This is very computationally expensive to do. It couldn't be done on a laptop, and none of the computer in the market was able to do this, so we actually have to build one. So as a poor medical student, I pulled out an Excel sheet and did a budget for food and rent for the next 3 months, and spent the rest on buying components to buy computers. My partner, friend, and family thought I was gone mad, but in retrospect, it was a good choice. As you can see, this is a computer that I built. You can see that there's 4 GPU, which is a high-performance computing chips. And being so close together, they get extremely hot, so you actually cool it with water. So at the bottom here, there's 2 pylons of water, and essentially they are glorified fish pumps. So this would circulate the water up into the chips, take away the heat, and in the back there's 2 giant radiators, like a car radiators, and 12 high-performance fans to take away the heat from the system. And this is what it looked like in the end. People always ask, why is the water blue and there's light? Or it's just for me, because I think it looks good. So this is the training process. Even with such a good computer, it would take 5 days to train the neural network. And I was going to my medical school as usual. On day 0, as you would expect, the model doesn't have any predictive ability. So the AUC was 0.5. And it rapidly increased only 1 day. It already reached an AUC of above 0.85. And 4 days later, it's plateaued out at 0.93. So as a little bit of calibration, as you can see today in some of the presentation, the human performance is anywhere between 0.5 to 0.75, depending on who you ask and which paper you look at. So this is an incredible step up in terms of predictive power for the model looking at time-lapse. An AUC of 0.93, what it really means is that when you randomly pick an embryo that would otherwise create a fetal heart, and randomly select another one which wouldn't create a fetal heart, the model would correctly score the positive embryo higher than the negative embryo 93% of the time. What this means is within a cohort of embryo for one particular patient, using the scoring, you will be doing the right thing by patient by picking the highest scoring embryo 93% of the time. One of the big challenges that we have here is, does this model translate across multiple labs or only one? And because we have contribution from 8 different labs across 4 different countries, what we performed was an 8-lab whole-out cross-validation. So in this process, we subsequently trained 8 different AI models. Each of them, we hold out data from 1 lab and then train the model on the other 7 labs, and never showing it the data from the whole-out lab. After the training has finished, we test the model on the data that was whole out and calculate the performance using AUC. And this table here shows that data. As you can see, the model really performed consistently across 8 different labs with various different cultures, lab methodologies, patient demographics, and so on. So this would demonstrate that the model is able to transfer knowledge across multiple lab conditions. We also built a software, and as you're pleased to know, you don't need to build a high-performance computer to run this. Once you finish the training, it could run on anything, such as a laptop. And we're looking to roll this out within Virtus. And given Vitrolife interest in time-lapse as well as artificial intelligence with their guided annotation product, I think it was quite natural progression that in April they announced the acquisition of the technology, and there will be a collaboration between Virtus, Harrison AI, and Vitrolife to continue to develop, validate, and bring this technology forward. And if you wonder when can I get this, it will come to one of your EmbryoScope in the near future, hopefully. And imagine the future where the hardware that you purchase today would get better through a software update and as the model continues to learn. So I think that's a very compelling vision of the future. So what's next? One of the problems with deep learning is that it's essentially a black box. Input time-lapse videos and outcome some score, and we're supposed to trust that. And that's not very comforting for a lot of people. So we've been trying to look inside this black box and basically ask, if IV is so predictive, what is it looking at? And surely, if it's outperforming its human counterpart, it must know something that we don't. So what you're seeing here is a visualization of heat map. Basically, the model is highlighting different parts of the video across time that it's particularly interested in. Blue is for, I'm not impressed by this. And red and orange is, this is good, thumbs up. So as you can see, on the top video, this is an embryo that creates fetal heart. It's highlighting the moral compaction, which we know to be such a crucial event in embryo development. And it was particularly happy about the cell division as well as the look of the blastocyst. Whereas at the bottom, it is also equally show interest across cell division. But then it was particularly unimpressed by the low-grade embryo blastocyst at the very end. So as you can see, the model is able to identify that things that embryologists would recognize as things that we know for such a long time completely by itself. Remember, we're never given it any particular information about grade, and it's rediscovered this through simulation within the computer. So this is really reassuring to see. The video here shows, if it's playing, this shows the real-time fetal heart prediction of the model. So not only it can give you one score for the whole video, it can actually give you the score at any particular point in time throughout incubation. So the x-axis shows time since insemination and Y is fetal heart. And as you can see, the model is allow the embryologist to see different dips, rise and falls of the score. So during that part, we can inspect and see what has happened to induce such a fall or rise of the score. And two, we haven't used all the data yet. Remember, time-lapse is not only the equator across time, it's also the z-stack, because time-lapse captures images at multiple focal plane. So the next progression of this work is to go to the fourth dimension and see if there's any performance left that we can extract from this system. And third is something I call the long tail problems, because common things happen commonly, but rare things rarely ever happen. So even with the data set of 10,000, you would expect that there are rare events that hasn't been captured by the data set, or at least captured in an inadequate amount to train the neural network. Things like cell debris, out focus, direct cleavage, and so on. So we want to continue to grow this data set. And if you're interested in this work, please contact Mark from Vitrolife if you want to contribute your data as part of this research. And that will allow this model to grow better. And I think it's the vision of the future where an algorithm shouldn't be assessed by how good it is today. It is how good it's going to be that really going to matter. And that comes from the training data and the continued development of the algorithms. And finally, we really want to get definitive proof for this by doing prospective study. So this year, we're conducting a RCT. The question we want to answer is, will IV reduce the time to pregnancy through better embryo selection? And we'll be comparing the IV AI software versus standard morphology grading. And with me to support this process, I bought an even bigger computer, and my family is saying I'm going mad again. The computer behind me there costs as much as a nice European car, I guess, and that's the reason why every conference I give, I wear the same suit, because I spend all my money on computer. So that's all, and thank you very much for your attention.